Welcome to EPG Pathshala. I am Aparna, working as scientist in MFPI Food Quality Control Laboratory, Professor Jaishankar, Telangana State Agricultural University. Now, we will learn about modes of heat transfer, determining the process time of heat transfer and the process lethality. It is very important to understand the modes of heat transfer, the processing time and also the process lethality so as to ensure that the heat preservation in the food processing takes place properly. As you all know, heat transfer is an operation that occurs repeatedly in the food industry for preserving one or the other kind of food matrices. Whether it is cooking, baking, drying, sterilization or freezing, heat transfer is an integral part of the processing of almost every food processing method. And an understanding of the principle that govern the heat transfer is very essential to make sure that the heat processing preservation is done in a very optimized manner. As you all know, food cannot be consumed in raw form. There are very few foods which can be consumed in raw form. For example, fruits, some of the vegetables and salads, etc. only can be consumed in raw form, whereas the other foods have to be cooked before being consumed. Now, for the food or the raw food material to be cooked, there is requirement that heat has to be applied to the food so that the raw food material becomes a cooked produce. As we all know, food can be cooked in different methods, and in all the methods, heat has to be applied. For example, when the food is being added directly into a pan which is hot, then the heat transfer takes place directly from the heated pan into the food. In some cases of cooking, for example, when you make puri or vada, etc., there is a hot oil medium which will transfer the heat into the food. Therefore, one is a direct method and one is an indirect method. Now, if you look at the heat transfer, it is nothing but simple transfer of heat at higher levels, at higher degrees of centigrade into the food matrix, where the conversion of raw food material gets converted into cooked food material. So, the heat transfer is a very important operation that occurs very often in the food industry. Heat transfer is a dynamic process in which the heat is transferred spontaneously from one body to another cooler body. The rate of heat transfer always depends upon the difference in temperatures between the bodies. The greater the difference in temperature, the greater is the rate of the heat transfer. Now, the temperature difference between the source of heat and receiver of the heat is therefore the driving force in the heat transfer anytime. An increase in the temperature difference increases the driving force and therefore increases the rate of heat transfer also. The heat passing from one body to another body travels through some medium which in general offers resistance to the heat flow. Both these factors, that is the temperature difference and the resistance to heat flow, affect the rate of heat transfer. As with other rate processes, these factors are connected by the equation as shown in the slide. That is, rate of heat transfer is equal to driving force divided by resistance. For heat transfer, rate of heat transfer is equal to temperature difference divided by heat flow resistance of the medium. During processing, temperatures may change and therefore the rate of heat transfer also will change. This is called unsteady state of heat transfer, in contrast to steady state heat transfer when the temperature do not change. An example of unsteady state heat transfer is the heating and cooling of cans in a retort to sterilize the contents. Unsteady state heat transfer is more complex since an additional variable, that is the time, enters into the rate equations. Heat can be transferred in three ways. They are by conduction, by radiation, and by convection. Let us try to understand each one of these, that is conduction, radiation, and convection. First one is conduction. In conduction, the molecular energy is directly exchanged from the hotter to the cooler regions. The molecules with greater energy communicating some of this energy to the neighboring molecules with less energy. An example of conduction is heat transfer through the solid walls of a refrigerated store. After understanding conduction, let us now move forward to radiation. Radiation is the transfer of heat energy by electromagnetic waves, which transfer heat from one body to another in the same way as electromagnetic light waves transfer the light energy. An example of radiation heat transfer is when a foodstuff is passed below a bank of electric resistance heaters that are red hot. After understanding radiation, let us now understand the third method of heat transfer, that is convection. Convection is the transfer of heat by the movement of group of molecules in a fluid. The group of molecules may be moved by either density changes or by forced motion of the fluid. An example of convection heating is cooking in a jacketed pot. Without a stirrer, density changes cause the heat transfer by natural convection. With a stirrer, the convection is forced. In general, heat is transferred in solids by conduction, in fluids by both conduction as well as convection. For calculations, it is often best to consider the mechanisms separately and then to combine whenever there is a necessity. In case of heat conduction, the equation will be rate is equal to driving force divided by resistance. This can be applied directly. The driving force is the temperature difference per unit length of heat transfer path, also known as the temperature gradient. Instead of resistance to heat flow, its reciprocal called the conductance is used. This changed the form of general equation to rate of heat transfer is equal to driving force into conductance. You can see the formula in the slide projected. Thermal processing implies the controlled use of heat to increase or reduce depending on the circumstances and the rates of reactions in the foods. A common example is the retorting of canned foods to effect the sterilization. The object of sterilization, as we all know, is to destroy the microorganisms, that is, bacteria, yeast, mold, in the food material to prevent decomposition of the food, which makes it unattractive or inedible. Also, sterilization prevents any pathogenic, that is, any disease-causing microorganisms from surviving and being eaten with the food. Pathogenic toxins may be produced during storage of the food if certain organisms are still viable in the food matrix. Microorganisms are destroyed by heat, but the amount of heating required for killing the different microorganism varies from food matrix to matrix as well as the amount of microorganism present in the food matrix. Also, many bacteria can exist in two forms, that is the vegetative form or the growing form and the spore or dormant form. The spores are much harder to destroy by heat treatment than the vegetative forms. Let us now try to understand thermal death time. It has been found that microorganisms including Clostridium botulinum are destroyed by heat at rates which depend on the temperature. Higher temperatures killing the spores more quickly. At any given temperature, the spores are killed at different times. some spores being apparently more resistant to heat than the other spores. If a graph is drawn, the number of surviving spores against the time of holding at any chosen temperature, it is found experimentally that the number of surviving spores fall asymptomatically to zero. Methods of handling the process kinetics are very well developed, and if the standard methods are applied to such results, it is found that thermal death of microorganisms follows for practical purposes what is called the first order process at a constant temperature. This implies that fractional destruction in any fixed time interval is constant. It is thus not possible, in theory at least, to take the time when all the organisms are actually destroyed. Instead, it is practicable and very useful to consider the time needed for a particular fraction of the organism which is to be killed. The rates of destruction can in a way be related to certain things. For example, it is related to the number of viable organisms which are present in the initial container or the batch of the containers. And it is also related to the number of viable microorganisms which can safely be allowed to survive. The surviving number must be small indeed, very much less than 1 to ensure adequate safety. However, this concept, which includes the admissibility of survival numbers of much less than 1 per container, has been found to be very useful. For such considerations, the ratio of initial to the final number of surviving organisms becomes the criteria which determines adequate treatment. A combination of historical reasons and extensive practical experiences has led to a number being set for Clostridium botulinum as 10 to the power 12 is to 1. For other organisms, under other circumstances, it will be different. The results of experiments to determine the times needed to reduce actual spore counts from 10 to the power 12 to 1 or to 0 is shown in the slide in the form of a figure. In this slide, you can see a graph, and in this graph, these times are plotted against different temperatures, and it shows that when the logarithms of these times are plotted against temperatures, the resulting graph is a straight line. The mean times on this graph are called thermal death times for the corresponding temperatures. Note that these thermal death times do not represent complete sterilization, but a mathematical concept which can be considered as effective sterilization, which is in fact a survival ratio of 1 is to 10 to the power 12 and which has been found adequate for safety. Any canning process also must be considered from the standpoint of effective sterilization. This is done by combining the thermal death time data with time temperature relationships at a point in the can that heats slowest. Generally, this point is on the axis of the can and somewhere close to the geometric center. Using either unsteady state heating curves or experimental measurements with a thermocouple at the slowest heating points in a can, the temperature time graph for the can under the chosen condition can be plotted. This curve has to be evaluated in terms of its effectiveness in destroying the Clostridium botulinum or any other critical microorganisms such as thermophilic spore formers, which are important in the food industry. In this way, the engineering data which provides the temperatures within the container as the processes is carried out and are combined with kinetic data to evaluate the effect of processing on the product. After understanding the thermal death time curve, it is important that other factor that must be determined so that the equivalent killing power at temperatures which are different from 121 degrees centigrade can be evaluated is the dependence of thermal death time on temperature. Experimentally, it has been found that if the logarithm of the thermal death time is plotted against the temperature, a straight line relationship is obtained. You can see the figure in which the thermal death time and the temperature relationships are shown. As you have seen from the slide, the formulas are given, the inputs in the formulas are explained in the slide. After understanding the thermal death time and the equivalent time, let us now try to understand the lethality calculations in terms of heat transfer. We have the general method. In sterilization of low acid foods, the process lethality is expressed as equivalent minutes at a reference temperature of 121.1 degrees centigrade and is commonly expressed as FO value. For example, the FO value of 6 minutes as shown in the figure which is being projected in the slide would assume a step change temperature response where the cold spot temperature would rise instantaneously to the reference temperature, be held there for 6 minutes and then cooled instantaneously. As shown in the figure, it is not possible for an in-container sterilization process. However, in the early research work, it was reported that lethalities which are attained at different temperatures are additive and thus may be accumulated as the temperature at the cold spot changes through a process. Thus, knowing the cold spot temperature history, one can determine the rate of lethality at each time increment, plot the resulting data as a function of time and integrate the curve to obtain the equivalent lethality at the reference temperature. You can see the figure which is projected in the slide. So if we look at the modes or methods of heat transfer, before understanding the methods of heat transfer, you also will have to take into account the thermal death time, the D value, the equivalent times, etc., so that the modes of heat transfer can be understood in a much better way. So after taking these calculations into consideration, the methods of heat transfer, that is conduction, convection and radiation, can be applicable to the desired food products and we can calculate the thermal death time curves to make sure that the food which is being processed by radiation, conduction and convection is up to the quality with least number of microorganisms. Now, general method calculations which remain the benchmark when determining the lethality delivered by any specific thermal processes through various methods of heat transfer. However, there are many mathematical models also which are reported in the literature which predict the process lethality which is based on heating, the modes of heat transfer and the cooling characteristics of the product and also the processing time and temperature data. You can make use of different mathematical models to calculate the heat transfer and to also calculate the process lethality for heat preservation of different kinds of foods. Finite difference analysis can be applied to determine both delivered lethality and quality which is lost during the heat processing. These techniques were actually published much before 1969, but currently we have lots of advanced techniques, lots of softwares and computers also have got the capacity to complete these calculations and you can apply them for various methods of processing. In today's chapter, you have learnt about the various methods of heat transfer. As we have already seen, we have three major methods of heat transfer, that is conduction, convection and radiation. These three methods are differently used for solid foods, liquid foods and in some cases the combination of these methods are used rather than the individual methods. For further information on these topics, you can refer to any textbook on principles of food preservation, heat and mass transfer textbooks, and for in-depth learning, you have to understand the calculations and practice the calculations by calculating the thermal death time, D values, etc. by taking live examples as given in the textbooks which you refer to. Thank you.